Hey guys, and here we're going to talk about heat transfer, energy associated specifically with physical changes. Now, we are supposed to understand the following objectives. We need to understand heat transfer is involved in physical changes. We need to be able to interpret a heating curve, be able to tell the melting and boiling points from the heating curve, use units such as joules and calories, and we are also going to perform calculations associated with temperature change within a single phase of an element or a substance. Here's a little heating curve simulation that we're going to briefly look at. You can click on this as well. And I don't know why this is taking so long. There we go. So this substance here, the blue, represents a solid, and we're going to heat it up as we go along. And as you see, the temperature increases. And then it levels off. And we take a look over here, we see that we have two different phases that are there. But the temperature is constant. So we look at that temperature as constant at that time at probably about 60 degrees Celsius. We heat that up and we get more and more of that liquid phase, the liquid being the red and the blue being the solid. But if you notice, that flat line as we go along is still constant temperature. And it's going to be constant temperature until we have melted everything. And then the liquid can heat up again. That's my melting point. And as you see, I'm heating up my liquid, and that temperature keeps on increasing up until a point where I start to produce gas. The gas is that yellow, represented by the yellow substance there. And again, I have another leveling off here of this until I'm all boiled. And then my temperature can increase again. So let's move back to the PowerPoint presentation. And we have our definitions here. The melting point, also known as the freezing point, is the same temperature depending on whether you're heating it up or cooling it down, similar to the boiling point and condensation point. Water is a substance that you are very familiar with, and we know water melts at 0 degrees Celsius when heating. It also freezes at 0 degrees Celsius if you're cooling. Water boils at 100 degrees Celsius while heating, and steam, which is gaseous water, condenses at 100 degrees Celsius while cooling. So here's the heating curve for water, and notice that we have these different leveling off points at 0 from when I'm going to ice to just liquid, and also when I'm going from liquid water to just gas. So that's a good diagram. You can read this, you can interpret the boiling point, melting point and boiling point just by where those plateaus occur while you're heating. Take a look at this axis and the x-axis. It's heating curve. It's how much heat is added. So our boiling point happens at 100 degrees Celsius, and our freezing point and melting point are at 0 degrees Celsius. So if you were to look at this graph, you can interpret the melting point and boiling point. Our melting point and freezing point is going to be where we have our first level off. So, and I'd estimate this to be about 1550 degrees Celsius for my melting point, and about, you look at your graph, and about 2700 or 2750 degrees Celsius for my boiling point. Now you can interpret that in all of these heating curves. Moving forward, let's talk briefly about energy change within a single phase of a substance. Now, specific heat just represents the ratio of energy to mass and temperature change of a substance. So, for instance, the specific heat of water, specific heat is the variable C, is equal to 4.184 joules per gram degree Celsius. This means that in order to increase the temperature of 1 gram of water by 1 degree Celsius, it requires 4.184 joules. And if you were to raise 1 gram of water by more degrees Celsius, it would take more energy. Likewise, if you wanted to raise more mass 1 degree Celsius, it would take more energy as well. So what we have is we have this formula which encompasses both mass and temperature change, where Q is my energy variable, M is my mass, C is my specific heat, and delta T is my temperature change. So Q is equal to M times C times delta T. Delta, just normally in science, when we see this delta, it looks like a triangle, is a Greek letter for the Greek letter D. It means change. And here we have a triangle which we can use as well. We're familiar with our triangles. Q is equal to MC delta T. So you can calculate any of these given the other three. Moving forward, let's say I want to figure out how much energy it takes to increase 25 grams of water from 10 degrees Celsius to 14 degrees Celsius. I can just outline it. I want to solve for my Q. Q represents energy, and I need my mass times my specific heat times my temperature change. And I can figure all those out with what's given. My mass is 25 grams. My specific heat is 4.184 joules per gram degree Celsius. Now that depends on the substance. Specifically for water, it takes that much energy. Water has a relatively high specific heat. And my temperature change is, I ended at 14 and I started at 10, so my change is 4 degrees Celsius. I can solve that out, and I can take 25 times 4.184 times 4, and I get 4,184 joules. If I want to solve for one of the other variables, I can do that pretty easily as well. In this instance, one adds 2,700 joules to 90 grams of aluminum at 20 degrees Celsius. And I want to know the final temperature. First, to do that, I need to find the change in temperature, delta T. And I can use algebra or my triangle to solve for delta T is equal to Q divided by the quantity, mass times specific heat. My heat, my amount of energy, is 2,700. My mass is 90. My specific heat of aluminum, like I said, is temperature dependent, is 0.90 joules per gram degree Celsius. So I just substitute in my equation for delta T, the variables that I know. And I have 27 joules divided by the product of 90 grams and 0.9 joules per gram degree Celsius. And what I get is that is 33.3 degrees Celsius. I'm not done yet, though, because look at what the question asks me. This is just my change in temperature. That's what I did first. My final temperature is 53.3 because I started off up here at 20 degrees Celsius. So we're going to be doing a lot of these problems, guys. So get used to them and figure out a way to either use the algebra or the triangle. But we're going to have to do these in class coming up soon. See you guys later.